Humanity is locked away, not in a basement or a bunker, but in a prison the size of the solar system, guarded by the most ruthless warden in the universe, the speed of light. 300,000 kilometers per second. Sounds fast, right? In reality, it is a snail's pace on a cosmic scale. The nearest star, Proxima Centauri, is at a distance of a little over 4 light years. That is approximately 40 trillion kilometers. If we launched a ship at the speed of the fastest human-made craft ever, Voyager 1, which rushes through interstellar space at a speed of 17 kilometers per second, the journey to our nearest neighbor would take 75,000 years. Think about it. By the time the ship reaches its goal, 3,000 generations will have changed on Earth. The pyramids will seem like yesterday's construction against the background of this term. The chemical rockets we are so proud of are a sentence to solitary confinement. They burn fuel, throw it overboard, and push us forward with pitiful efficiency. The problem is not just speed, the problem is the very nature of motion. Imagine you are pushing a cart in a supermarket. The faster you go, the harder it is to accelerate further. This is because your muscles get tired and the cart resists acceleration. Now imagine that with every step you take, the cart becomes heavier. At first, not by much, then twice as heavy, then 10 times, 100, 1,000. When you run at the limit of your strength, it already weighs 1,000,000 tons. This is the relativistic mass increase. The faster you move, the heavier you become, and the more energy is required for further acceleration. At a speed close to light, your mass tends to infinity, and infinite mass cannot be accelerated by any force in the universe. Physicists long believed that this was an iron curtain, an impassable boundary between us and the stars. Interstellar travel seemed like a dream fit only for science fiction novels. But in 1994, Mexican physicist Miguel Alcubierre noticed something strange. Einstein forbade moving through space faster than light, but the equations of general relativity themselves say nothing about the speed at which space itself can expand or contract. The universe is expanding faster than light right now, and no one blinked an eye. So, there is a loophole. What if we create a wave in the very fabric of reality? What if, instead of flying through space, we make space move us? Now we will analyze how the most beautiful physical concept of the 21st century works, the Alcubierre drive. We will talk about why the universe might categorically forbid us from using this technology. And we will find out why a ship with a warp drive is not a means of exploration, but potentially the deadliest weapon imaginable. But before we dive into the details, let's understand why ordinary acceleration is a dead end. By the way, if you are interested in such topics, subscribe to the channel and give a like. We regularly analyze the most exciting questions of space and physics. And believe me, there are many more incredible stories ahead. And now, let's plunge into Einstein's tyranny. At the beginning of the 20th century, physicists faced an unpleasant truth. The faster an object moves, the more time and space around it are distorted. This is not a philosophical abstraction. This is a measurable, verified, absolutely real effect. When a particle in an accelerator speeds up to 99% of the speed of light, it begins to behave as if its mass has increased 7 times. At 99.9% of the speed of light, the mass increases 22 times. At 99.99, 70 times. The graph looks like a vertical wall. The closer to the speed of light, the steeper the climb. At the speed of light itself, the mass tends to infinity. Infinity is not just a very large number. It is a conceptual limit, a mathematical abyss. No engine, no energy source, even if you gathered all the matter in the universe and turned it into fuel, could push a massive object through this barrier. Let's try to visualize this through a familiar image. Imagine you are rolling a heavy metal ball along a concrete road. At first, everything goes normally. You push, the ball rolls. Now imagine that with every meter of the way, the ball absorbs the surrounding air. At first, it just gets heavier. Then it starts sucking in dust, pebbles, pieces of asphalt. You push harder, and it continues to grow. After a kilometer, it is already the size of a car, and you can barely cope. After 10 kilometers, it is a truck, and no muscles in the world will move it. And now imagine that the growth does not stop. It begins to suck in buildings, trees, lakes. It becomes the size of a mountain, a continent, a planet. You are still trying to push it, but it is pointless. Its mass is already greater than the mass of the entire Earth. That is what happens to objects approaching the speed of light. The universe adds weight to your every movement, making further acceleration increasingly absurd, and you haven't even gotten close to the speed of light. Physicists call this inertia. The greater the mass, the greater the inertia, the more the object resists a change in speed. But where does this extra mass come from? The thing is, mass and energy are two sides of the same coin. Einstein's famous formula, energy equals mass times the square of the speed of light, says exactly this. Energy can turn into mass, and mass into energy. When you accelerate a particle in an accelerator, you pour energy into it. This energy does not disappear. It turns into additional mass. The faster the particle, the more energy is stored in it, the heavier it becomes. It is like pouring water into a bottomless barrel. The more you pour, the heavier the barrel, but the water level hardly rises. Now let's imagine a specific situation. Suppose we want to send a starship to Alpha Centauri, our nearest stellar system, located at a distance of a little over 4 light years. We decide that we want to get there in a reasonable time, say, in 10 years by the ship's clock. To do this, we need to fly at about half the speed of light. Fine, you think, we will build a powerful enough engine. But the problem is that fuel also has mass. To accelerate the ship and the fuel, even more fuel is needed. And this additional fuel also needs to be accelerated, which means even more fuel is required. This is called the Tsiolkovsky rocket equation, and it is ruthless. Calculations show that to reach even 10% of the speed of light with chemical rockets, you would need so much fuel that the mass of the ship with fuel would exceed the mass of all the planets in the solar system combined. And for 50% of the speed of light, the numbers become so absurd that they are even embarrassing to write down. Physicists have tried to circumvent this problem for decades. Nuclear engines are better than chemical ones, but not enough. Thermonuclear fusion could theoretically give a speed of up to 10% of the speed of light, but that still means hundreds of years in transit. Antimatter has fantastic efficiency, 100% conversion of mass into energy. But where to get antimatter on an industrial scale? Even if we solved all the technical problems, even if we built the perfect engine with perfect efficiency, we still run into a fundamental limit, the speed of light. The universe has set a hard limit on the speed of transfer of information, matter, and causality. This barrier is not technical, not engineering. It is fundamental. It is woven into the structure of reality itself. But there is one nuance. Einstein forbade objects from moving through space faster than light. He said nothing about the speed of space itself. Think about it this way. If you are standing on an escalator at the airport, you are not walking. The escalator is moving, and you are just standing on it. But relative to the airport floor, you are moving. Now imagine that the escalator is moving faster than you can run. A person walking on the floor next to the escalator sees that you are overtaking them, even though you yourself are standing still. This is not a violation of the rules. The rules forbid you from running faster than a certain speed, but they say nothing about the speed of the escalator. Space is the escalator. The universe is expanding right now. Moreover, some of its parts are moving away from us faster than the speed of light. Galaxies at the edge of the observable universe are running away at a speed several times higher than the speed of light. This does not violate the theory of relativity because the galaxies themselves do not move through space faster than light. The space between us and them moves. The difference seems subtle, but it is critical. Locally, nothing moves faster than light. Globally, distances grow at any speed that conditions allow. So, if you create an artificial wave of expansion and contraction of space, you can ride it and rush through the cosmos while formally staying in place. This is exactly what Alcubierre proposed. But how to do this? How to make space move at your command? The answer lies in Einstein's equations, the very ones that describe how matter and energy curve space-time. The mass of the Earth curves space around itself, creating what we call gravity. A black hole curves space so strongly that even light cannot escape. Alcubierre realized that if energy is correctly distributed around the ship, an asymmetric curvature can be created. The space in front of the ship will contract, and the space behind it will expand. The ship will be inside a bubble of normal flat space, and this bubble will slide along a wave of deformed reality. Inside the bubble, nothing moves faster than light, but the bubble itself can rush at any speed, even 1,000,000 times faster than light. You sit in a chair, sip coffee, and the distance to the stars melts before your eyes. A journey to Proxima Centauri, which was supposed to take 75,000 years, is reduced to a few days, perhaps even hours. Sounds like magic, but it is pure physics. Einstein's equations allow such a configuration of space-time. The mathematics checks out. A solution exists. However, there is one tiny problem. To create this bubble, you need something that does not exist in nature. Something so strange and unnatural that most physicists do not believe it can exist at all. And even if we found a way to create it, the consequences of using a warp drive would be catastrophic. But more on that a bit later. For now, let's look at how humanity came to the idea of a warp drive. History is full of attempts to bypass the light barrier, and each of them failed for the same reason. We tried to move faster, but we needed to change the game itself. 20th century physics gave us quantum mechanics, the theory of relativity, and nuclear energy. But it also closed the door to interstellar travel, declaring the speed of light an absolute limit. In the 50s and 60s, at the peak of the space race, engineers were full of optimism. Project Orion proposed accelerating a ship with a series of nuclear explosions behind the stern. Explosion after explosion, like a giant cannon firing at its own bottom. Calculations showed that such a ship could reach several % of the speed of light. The problem was political and technical. Few people wanted to launch thousands of nuclear bombs into space, and controlling such a ship would be incredibly difficult. The next idea was the Bussard ramjet. The concept was elegant. A huge funnel collects rarefied hydrogen from the interstellar medium, compresses it, ignites a thermonuclear reaction, and uses the released energy for acceleration. Fuel is free and always at hand. Sounds perfect. In practice, it turned out that the interstellar medium is too rarefied. Only 1 atom per cubic centimeter. The funnel would have to be the size of a planet to collect enough matter, and the resistance of this funnel while moving through space would create more drag than the engine could compensate for. A dead end. There were also completely exotic ideas. Photonic sails, giant mirrors pushed by laser beams from Earth. Project Breakthrough Starshot plans to accelerate microscopic probes to 20% of the speed of light. Precisely so. But this only works for tiny objects, not for ships with people. Antimatter is theoretically ideal, practically unattainable. We produce antimatter in microscopic quantities, and the cost of 1 gram is measured in trillions of dollars. All these concepts ran into the same ceiling. Even if we solved all the engineering problems, we cannot overcome the relativistic mass increase. An attempt to accelerate a ship to the speed of light requires infinite energy. Full stop. End of story. But physicists do not like to give up. In the mid-80s and early 90s, the study of exotic solutions to Einstein's equations began. Wormholes, bridges between different points of space-time. Theory allowed their existence, but they required exotic matter, a substance with negative mass or negative energy density. No one knew if such matter existed. Most physicists thought not. But the equations were stubborn. They said, if exotic matter exists, wormholes are possible. And if wormholes are possible, then you can travel between stars instantly, without acceleration, without the light speed barrier. And then Miguel Alcubierre appeared, a young Mexican physicist working on a doctoral dissertation at Cardiff University in Wales. He was a fan of Star Trek, the same series where the ship Enterprise uses a warp drive for faster-than-light travel. Alcubierre wondered, what if the warp drive was not just a fiction of scriptwriters? What if it could be described mathematically within the framework of general relativity? He sat down at Einstein's equations and began to play with the metric of space-time. A metric is a mathematical object describing how distances and times are measured in curved space. Alcubierre set out to find such a metric in which a ship could move faster than light without violating the laws of physics. After several months of work, he found a solution. He published it in 1994 in the journal Classical and Quantum Gravity. The article was simply titled, Warp Drive, Hyperfast Travel Within General Relativity. Alcubierre's solution described a space-time in which the area behind the ship expands and the area in front contracts. The ship is inside a bubble of flat space that slides along this wave of deformation. Inside the bubble, space remains normal, flat, Minkowskian, as physicists call it. No curvatures, no relativistic effects. Time flows normally. You do not feel acceleration because you are not accelerating relative to your local space. You just sit in the bubble, and the bubble carries you faster than light. It is like standing on a moving walkway at the airport. You are not walking, but you are moving. Only the walkway moves faster than you could run. The scientific community reacted with a mixture of admiration and skepticism. On the one hand, the mathematics was flawless. Alcubierre's metric satisfied Einstein's equations. On the other hand, creating such a deformation required exotic matter, the same one with negative energy density. It was like saying, yes, you can build a time machine if you find a piece of matter that weighs -1 kilogram. Theoretically possible, practically absurd. But the idea stuck. Physicists began to dig deeper, check, analyze, and modify. And this is where the story gets really interesting. So we have a concept. Now let's look at the mechanics, exactly how the warp bubble works. Imagine an ocean wave. The water in front of the wave crest rises, creating an elevation. Behind the crest, the water sinks, creating a hollow. The wave moves forward, but the water itself mostly stays in place. It just rises and falls. A surfer stands on the crest and is carried forward not because they are swimming, but because the wave is moving under them. The warp drive works similarly, only instead of water, it is space itself. Alcubierre proposed creating a wave in the fabric of space-time. In front of the ship, space contracts. This means that the distance becomes shorter. Imagine you draw 2 points on a rubber sheet and then crumple the sheet so that the points are closer to each other. The distance between the points has decreased, although the points themselves did not move. Behind the ship, space expands, distances increase, as if you are stretching the rubber sheet. The ship is between these two zones in an area of flat, normal space. This is the bubble. Now, the most important part, the ship does not move inside the bubble. It stays in place relative to its local space, but the bubble moves. Contraction in front and expansion behind create a gradient, a wave that pushes the bubble forward. The speed of this wave is not limited by the speed of light because it is not motion through space. It is the motion of space itself. Imagine you are standing on a treadmill in a gym. The belt is moving and you are standing, but relative to the floor, you are moving. Now imagine that the belt can move at a speed of 100 kilometers per hour, 1,000, a million. You are not running, you are standing, but relative to an outside observer, you are rushing faster than light. This explains why there are no g-forces inside the bubble. When you accelerate in the usual way, by chemical rocket, nuclear engine, or even photonic sail, you feel acceleration. This is a force pushing you forward. Your body resists the change in speed, and you feel pressure in your chest and heaviness in your limbs. In a warp bubble, there is nothing like that. You are not accelerating relative to your local space. You are in free fall along a geodesic line. This is a physical term meaning that you follow a natural trajectory in curved space-time. Imagine you are floating down a river. The water carries you, but you do not feel jolts because you are moving with the water. A warp bubble is a current in the ocean of space-time. Here is an analogy that makes this even clearer. Imagine a large airport with moving walkways. You are standing on one of them with a suitcase and a cup of coffee. The walkway is moving at a speed of 5 kilometers per hour. You are not walking, just standing. Next to you, on the regular floor, another passenger is walking at a speed of 4 kilometers per hour. They are not catching up to you. You are overtaking them, even though you are standing still. The coffee in your cup does not spill because you are not accelerating. You and the walkway move as a single unit. Now imagine that the walkway suddenly accelerates to 100 kilometers per hour. You are still standing in place relative to the walkway, but relative to the airport floor, you are rushing faster than a person can run. The coffee still doesn't spill because there is no acceleration in your frame of reference. And now let's make the walkway even faster. 1,000 kilometers per hour, 10,000, 100,000. The speed of light, twice as fast as light, 100 times as fast. You are still standing, the coffee is still in the cup, but relative to the outside world, you are overtaking light itself. This is the warp drive. Space-time is the walkway. You stand still, the walkway carries you. And the walkway can move at any speed because the rules of the theory of relativity apply only to objects moving through space, not to space itself. Another image. Imagine the universe is a huge cloth stretched in all directions. Your ship is a ball lying on the cloth. Ordinary motion is when you push the ball and it rolls on the cloth. The faster it rolls, the more friction, the more resistance. Warp drive is when you do not touch the ball, but instead take the cloth and start moving it. You crumple the cloth in front of the ball and stretch it behind. The ball stays in place relative to its local section of cloth, but the cloth itself moves, carrying the ball with it. There is no friction because the ball is not rolling. It is just sitting in a fold of the cloth that slides forward. Mathematically, this is described by the Alcubierre metric, a set of equations determining the geometry of spacetime around the ship. The key parameter is the shape function of the bubble, which describes how much space contracts in front and expands behind. If this function is correctly tuned, a bubble with very thin walls and a flat interior can be created. Inside the bubble, space remains ordinary and Euclidean, like in school geometry. No, on the boundaries of the bubble, the curvature is enormous. It is this curvature that creates the effect of motion. The stronger the curvature, the faster the bubble moves. In principle, the metric can be adjusted so that the bubble moves millions of times faster than light. The journey to Andromeda, our neighboring galaxy located 2.5 million light-years away, could be completed in a few days. Sounds like science fiction, but it is a solution to Einstein's equations. Mathematics does not lie. The problem is not in the equations. The problem is that to create such a bubble, you need to break one of the most fundamental rules of physics. You need something that weighs less than nothing. Something with negative mass. Something that, as far as we know, does not exist. So we have come to the strangest part of the story: exotic matter, the fuel that isn't there. Alcubierre realized that to create an asymmetric curvature of space, contraction in front and expansion behind, a special type of energy is needed. Ordinary matter and ordinary energy curve space the same way in all directions. The mass of the Earth creates a gravitational pit that attracts everything around it. The mass of the Sun curves space-time so that the planets move in orbits. No, these curvatures are symmetrical. To create asymmetry, to compress space in one direction and stretch it in another, you need matter with negative energy density, or, simply put, negative mass. What does negative mass even mean? Imagine an ordinary object, say a stone. It has mass. If you push the stone, it will fly in the direction you pushed it. This is intuitively understandable. Now imagine an object with negative mass. If you push it, it will fly in the opposite direction, not toward the push, but away from it. This sounds absurd, but mathematically it is quite consistent. An object with negative mass has negative inertia. It accelerates in the direction opposite to the applied force. Gravitationally, it also behaves strangely. It does not attract other objects, it repels them. Imagine you throw an apple up, and instead of falling back, it flies away into space because the Earth repels it instead of attracting it. An even stranger thing happens when an object with positive mass and an object with negative mass are side by side. Positive mass is attracted to negative mass, and negative mass is repelled by positive mass. The result, they start chasing each other. Positive mass flies toward negative, but negative runs away at the same speed. They accelerate to infinite speed in finite time. This violates the law of conservation of energy. Therefore, most physicists believe that negative mass cannot exist in nature. It is a mathematical possibility, but a physical impossibility. The universe, it seems, forbids it. But there is a subtle point. Alcubierre does not need negative mass in the literal sense. He needs negative energy density. This sounds almost as strange, but there is a difference. Energy density is the amount of energy in a unit of volume. Ordinary matter has positive energy density. Even a vacuum, absolutely empty space, has zero or slightly positive energy density due to quantum fluctuations. But quantum mechanics allows situations where energy density becomes negative relative to the vacuum. This is called exotic matter. It does not have negative mass, but locally, it has less energy than the vacuum. Sounds like a play on words, but it is important. The only known phenomenon that produces something like exotic matter is the Casimir effect. It was predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in the 90s. The essence is as follows. If you take two conducting plates and place them very close to each other in a vacuum at a distance of a few nanometers, they will begin to attract. Why? Because only certain quantum modes of vacuum fluctuations, virtual particles that constantly appear and disappear in the vacuum, can exist between the plates. Outside the plates, all modes are allowed. Inside, only some. The difference in pressure of virtual particles creates a force pushing the plates together. This is a real, measurable effect. At a distance of 10 nanometers, the Casimir force creates a pressure of approximately 1 atmosphere. What's interesting is that the energy between the plates is lower than the energy of the vacuum outside. This is negative energy density, but only relative to the surrounding space, not absolute. If we take the energy of the vacuum as zero, then the energy between the plates will be slightly negative. Physicists immediately wondered, can the Casimir effect be used to create a warp drive? Maybe it is possible to build a huge structure of plates that generates enough exotic matter to curve space-time in the right way. Unfortunately, the scales are deadly. The density of negative energy in the Casimir effect is negligible, about 10 to the power of minus 24 joules per cubic meter. This is 100,000 billion times less than the energy density of ordinary matter. To create an Alcubierre bubble the size of a starship, you would need an amount of exotic matter equivalent to the mass of the entire observable universe multiplied by -1. Even taking into account various optimizations, thinner bubble walls, oscillations of shape, the use of external gravitational fields, the requirements remain astronomical. One of the optimizations proposed by Chris van den Broek at the end of the 90s showed that the required mass of exotic matter could be reduced to several solar masses. This is huge progress compared to the mass of the universe, but still absurdly much. Where to get several solar masses of negative energy? How to collect it, hold it, direct it? Moreover, no one knows if it is possible at all to create exotic matter in macroscopic quantities. The Casimir effect works on nanometer scales under laboratory vacuum conditions. It is a quantum effect, and it disappears when scales increase. Attempts to scale it up to the size of a ship run into fundamental limitations of quantum field theory. Some physicists suggest that quantum inequalities, mathematical constraints imposed on energy density by quantum fluctuations, might completely forbid the existence of macroscopic exotic matter. If this is true, warp drive is impossible not for engineering but for physical reasons. The universe simply does not allow the right type of energy to exist. But let's assume we found a way to bypass this limitation. Suppose that future generations discover a new source of exotic matter, maybe through manipulation of dark energy, which fills the universe and accelerates its expansion. Dark energy has negative pressure, which is mathematically equivalent to negative energy density under certain conditions. If we could learn to concentrate and direct it locally, it could be used for a warp drive. Or perhaps quantum gravity will open new paths, such as the manipulation of quantum fluctuations of spacetime on Planck scales, where classical geometry stops working. This is pure speculation, but no more fantastic than the idea of a warp drive itself. Suppose we solved the problem of exotic matter. We built a generator, created a bubble, turned on the engine. The ship starts moving. Space contracts in front, expands behind. Everything works. We are rushing to the stars faster than light. A journey that was supposed to take millennia fits into a few days. Incredible, right? But then a question arises that makes physicists clutch their heads. What if a warp drive is a time machine? The theory of relativity states that any faster-than-light motion is equivalent to traveling back in time. This is not a metaphor, not a philosophical discussion. This is a rigorous mathematical consequence of the structure of space-time. Imagine you send a signal faster than light from Earth to a star 10 light-years away. For an observer on Earth, the signal arrives instantly, or almost instantly. But for another observer moving relative to Earth, the signal might arrive before it was sent. This sounds absurd, but it is a direct consequence of the relativity of simultaneity. The notion that events simultaneous for one observer are not simultaneous for another. Now imagine you use a warp drive to travel to a distant star and then back. For you, a few days have passed. Now, because of relativistic effects, you might return to Earth before you left. You meet yourself in the past. You can change the events that led to your journey. You can create a time paradox. Physicists call this the problem of closed time-like curves. A closed time-like curve is a trajectory in space-time that returns to the same point in space and time from which it began. It is a loop in the fabric of reality, allowing you to interact with your own past. A classic example, the grandfather paradox. Imagine you travel back in time and kill your grandfather before he met your grandmother. Then your father or mother will not be born, which means you will not be born either. But if you don't exist, who killed your grandfather? A paradox. The timeline falls apart. The universe is entangled in its own logic. Physicists long considered this a purely theoretical curiosity with no relation to reality. But warp drive makes this problem very specific. If a warp drive can create a closed time-like curve, then it is a time machine, and time machines lead to paradoxes. Stephen Hawking, one of the greatest physicists of the 20th century, proposed the chronology protection conjecture. He formulated it jokingly. The laws of physics do not allow time travel. This makes the world safe for historians. The idea is that whenever you try to create a time machine, whether through a wormhole, a warp drive, or any other method, the universe finds a way to stop you. Quantum vacuum fluctuations accumulate on the boundaries of the time machine, creating an infinite energy density that destroys the very structure of space-time. The time machine self-destructs at the moment of activation. This is an unproven theorem, a hypothesis, but there are strong reasons to think it is true. In the case of a warp drive, the problem may be even more fundamental. Calculations show that when a warp bubble reaches faster than light speed, event horizons form on its boundaries, similar to the horizons of a black hole. Everything that falls behind this horizon cannot escape. The ship's crew finds themselves locked inside the bubble, unable to interact with the outside world. Signals do not pass through the horizon. The ship becomes an isolated bubble of reality, torn away from the rest of the universe. Moreover, quantum fluctuations begin to accumulate on the horizon, creating Hawking radiation, thermal radiation arising from quantum effects near event horizons. The temperature of this radiation can be enormous. Calculations give a value on the order of 10 to the power of 32 Kelvin. This is billions of times hotter than the center of the sun. The ship's crew will be instantly incinerated. The bubble will become unstable and collapse. This means that warp drive is perhaps physically impossible, not because we don't know how to create exotic matter, but because the universe actively resists its existence. As soon as you try to create the conditions for faster-than-light travel, quantum effects destroy your construction. The chronology protection conjecture suggests that this is not an accident, but a fundamental feature of physics. The universe is designed so that causality, the principle that the effect always happens after the cause, is protected at the deepest level. You cannot create a time machine because the very structure of space-time forbids it. Of course, we don't know for sure. We don't have a complete theory of quantum gravity. Perhaps when we understand how to combine general relativity and quantum mechanics, it will turn out there is a way to bypass these limitations. Perhaps exotic states of matter or space-time exist that allow faster-than-light travel without time paradoxes. But at the moment, everything points to the fact that the universe said a firm no. You can dream of a warp drive. You can write equations describing its operation, but as soon as you try to build it, reality will rebel. And even if we somehow bypassed all these problems, if we found exotic matter, stabilized the bubble, and avoided time paradoxes, we would still have one last, perhaps the most terrifying problem. A problem that turns the warp drive from a means of exploration into a weapon of mass destruction. While we fly at warp speed, the bubble interacts with the surrounding space, and space, as it turns out, is not empty at all. The interstellar medium contains about 1 hydrogen atom per cubic centimeter. Sounds negligible, but when you rush faster than light, these atoms become a problem, a serious problem. Imagine you are driving a car on a road during heavy rain. Water drops hit the windshield with considerable force, right? Now imagine you accelerate to 100 kilometers per hour, 200, 500. At a very high speed, even raindrops start piercing the glass like bullets. They haven't changed. It is just water. The relative collision speed has changed. The same thing happens with a warp bubble. Hydrogen atoms in space are stationary relative to the surrounding space, but when a warp bubble rushes past them at faster-than-light speed, these atoms fall into the curved region of space-time on the bubble's boundary. What happens to them? They are captured. The deformation of space-time works like a giant funnel. Particles falling into the area in front of the bubble experience a monstrous blue shift, a relativistic effect where particle energy increases due to the observer's motion. In the case of a warp drive, this shift is not just large, it is astronomical. A hydrogen atom, which at rest has an energy of less than 1 electron volt, can, after being captured by the bubble, receive an energy equivalent to gamma radiation. This is no longer harmless hydrogen. This is a cosmic projectile flying at near light speed and carrying enough energy to destroy atomic nuclei. But that's only the beginning of the story. Particles are not just captured, they get stuck. The event horizons forming on the boundaries of a faster-than-light bubble act as a trap. A particle that falls inside a certain zone cannot escape. It continues to move with the bubble, accumulating in the front part like trash on the bow of a ship going through dirty water. The longer the journey lasts, the more particles accumulate. One atom after another, million after million, trillion after trillion. Each of them carries energy many times exceeding its rest energy. Now imagine what happens when you decide to brake. The ship approaches the target star system. You begin to reverse the deformation of space, expanding in front, contracting behind. The bubble's speed drops. It transitions from faster than light speed to light speed, then to near light speed, and finally to sublight speed. At the moment the bubble becomes sublight, the event horizons disappear, the trap opens, and all the particles accumulated during the journey are released simultaneously. They shoot forward in a dense, concentrated beam, directed right where you were flying, that is, toward the planet you were heading for. The energy of this beam depends on the duration of the journey and the bubble's speed. Physicists Brendan McMonagle, Geraint Lewis, and Philip O'Byrne from the University of Sydney conducted a computer simulation in 2012. Their conclusions were shocking. Even for a relatively short journey, say, a few light years, the amount of accumulated energy is equivalent to the explosion of hundreds of supernovae. When the bubble breaks, this energy is released in fractions of a second, crashing into the target area like a tsunami of gamma radiation and relativistic particles. Everything in the path, planets, moons, space stations, will be sterilized instantly. The atmosphere will burn out, oceans will boil, and the surface will turn into molten lava. This is not a side effect. It is an inevitable consequence of warp drive physics. Analogy. Imagine a snowplow driving on a snowy road. It scrapes up snow in front of itself, accumulating it on the blade. The further it goes, the more snow. When the snowplow stops and lifts the blade, all the accumulated snow falls forward in a huge pile. Now imagine that this is not snow, but energy equivalent to thermonuclear explosions. And instead of a road, it is space. And instead of a pile of snow, it is a beam of deadly radiation directed at an inhabited planet. Calculations show there is no upper limit to the accumulated energy. The longer the journey, the more particles are captured, the higher the beam's energy. A journey across the entire galaxy could create a beam with energy comparable to a quasar, the brightest object in the universe. When such a ship breaks at a planet, it does not arrive as a guest. It arrives as an apocalypse. Any civilization waiting for a meeting will be destroyed the moment the ship arrives. Not because someone wants this, but simply because such are the laws of physics. Warp drive is not a means for travel. It is a weapon. Worse still, it is impossible to control the direction of the discharge. Accumulated particles are concentrated in the front of the bubble, and when the trap opens, they fly strictly forward where the ship was directed. An attempt to deflect the beam would require changing the trajectory of the entire bubble at the moment of braking, which is technically incredibly difficult. Simply put, if you fly to a planet, you inevitably shell it upon arrival. The only way to avoid this is to brake at a great distance from the target and then fly to it by ordinary means. But then why is a warp drive needed at all if you spend centuries on the last part of the way? There is another eerie detail. Radiation accumulates not only in front. Inside the bubble itself, at its boundaries, unpleasant things also happen. Hawking radiation generated by event horizons creates extreme temperatures. The ship is inside flat space, protected from direct impact, but the walls of the bubble are literally boiling with quantum fluctuations. If the bubble is not stable enough, this radiation can leak inside, frying the crew. Imagine a microwave oven working at maximum power, only instead of food, you are inside. No material can withstand such temperatures. Even if we find a way to shield the ship, the energy costs for maintaining the protection will be monstrous. But let's assume we solved all these problems. found exotic matter, stabilized the bubble, protected the crew, and learned to brake safely. The question remains, is it worth it? Interstellar travel is not just a technical challenge. It is a philosophical question about humanity's place in the universe. Think about this. The nearest potentially habitable exoplanets are at a distance of 10 to 100 light years. Even with a warp drive, if it works, the journey will take time. And every journey carries a risk. The risk of bubble instability, the risk of meeting unexpected obstacles, dark matter, dense clouds of interstellar gas, gravitational anomalies, the risk that we haven't accounted for something in the calculations and the ship will simply collapse into a point or stretch into infinity. Who would want to risk their life knowing that technology at best balances on the edge of physical possibility? Moreover, even if a warp drive works, it only solves the problem of distance. It does not solve the problems of biology. The human body is not adapted for interstellar travel. Radiation, microgravity, psychological isolation, all this remains. Warp drive makes the journey fast but unsafe. Maybe it is wiser to send robots or digital copies of consciousness uploaded into computers, or to give up the idea of physical travel altogether and develop technologies for long-distance communication, observation, and studying the universe from a safe distance. And then there are alternatives. Not all of them require violating the laws of physics. Generation ships, where people live and reproduce for centuries while the ship flies to the stars. Animation, cryogenic freezing of the crew for the duration of the journey. Sublight ships with thermonuclear engines capable of reaching 10 to 20% of the speed of light. Slower than warp drive, but physically achievable. Each of these ideas has its problems, but none requires exotic matter, creates time paradoxes, or turns the ship into a space weapon. Perhaps the universe is designed precisely so that interstellar travel is difficult. Not impossible, but difficult enough that only a truly developed, wise civilization could carry it out. The speed of light barrier is not a prison. It is a filter. It weeds out civilizations that are not ready for a meeting with others. It makes us develop slowly, carefully, and deliberately. Maybe it's for the better. Warp drive remains one of the most beautiful ideas of theoretical physics. It shows that Einstein's equations are richer than we thought, that the universe leaves loopholes even in the strictest prohibitions. No, the beauty of an idea does not make it realizable. We can write equations describing a bubble, but we cannot create it. Not now, perhaps never, and that is normal. Humanity has always dreamed of the stars. But maybe the way to them lies not through cheating the laws of physics, but through understanding them. Not through warp drive, but through patience. Not through speed, but through perseverance. We may not see other stars in our lifetime, but our descendants in hundreds or thousands of years might reach them. And when they do, they will know they came there not as conquerors, not as accidental destroyers, but as researchers who have traveled a long way. A slow way, the right way. Thank you for being with me on this journey through physics, paradoxes, and dreams of faster-than-light flights. If it was interesting to you, subscribe to the channel and give a like. There are many more incredible stories ahead about space, time, and the limits of the possible. See you in the next video.